So once again, I'm really pleased today. It's Friday again. My name is Christian Sasser. I'm the astronomer in charge for iTelescope. And today, I'm really pleased to introduce to you Dr. Liza Sazonova, who is a post fellow at the University of Waterloo. At the moment, she is, however, in Nottingham in the UK. So Lisa, welcome.
Hi, everyone.
That's very nice. It's very nice to have Lisa here. So we're going to hear all about the evolution of galaxies, or actually more about dying galaxies. I've just been talking to Lisa, and she says today the evolution or the classification of galaxies is very sophisticated. So I think it's probably a bit like how you would classify species in biology just before the DNA, where you look at all the characteristics, what's the beak, the eyes, and all that like. And that's what they do with very sophisticated instrumentation. I hope I got that right.
Yeah, it's actually very similar. Thanks for the summary.
Okay, Lisa, well, welcome. And don't be shy, just talk a lot about yourself too, because we really want to know what you do and how you came into the field, and the floor is all yours.
Great, thank you. Let me just share screen. So are you all seeing what I'm seeing?
We are. Go ahead. Yes.
Great. So thank you all for coming. It's amazing to see so many people from so many different parts in the world who are equally excited to listen about space and galaxies and things like that. I know you're all science and space enthusiasts, being subscribers to the iTelescope website, and I hope I can just talk you through a little bit about what are galaxies, how do they live, how do they die, what are we looking at when we all take beautiful pictures of these objects in the night sky. I'm starting with, I think, one of the best images astronomers have ever taken, and I will talk more about it. But if there's one thing you should take out of this talk, is that space is beautiful. Please continue taking pictures of it. It's great. It's great to give talks about space because I can show you lots of images, and it's exciting. So before I go on and talk about interesting things, I'll say a couple of words about myself. This is me. I'm also on your screen. My name is Liza Sazonova. I am originally from Moscow, Russia. You have probably seen lots of really scary looking pictures of Moscow. It's actually a beautiful place. This is a park right next to where I grew up. It's very peaceful and nice, and I recommend everyone visit if you can, if life is a bit better there soon. I finished my PhD this summer at Johns Hopkins University in the US. So being doctor is very new to me, and this is the first talk I give as a doctor, so I'm very excited about that. And I am going on to do my postdoctoral fellowship, as Christian said, at the University of Waterloo in Canada. Also another beautiful place, very famous for its geese, so I can't wait to move to Canada and feed some geese there. That is my hobby. I am a contributing author to Astrobytes. This is a Reader's Digest where graduate students and postdoctoral fellows like me go and read new modern research that's coming out every day, and we write short summaries of what these papers are about. So if you want to learn a little bit more about modern astronomy research, but reading papers is challenging even for me, Astrobytes is a very good resource to try to get an easily explained summary of these things. This is a galaxy. We live in the galaxy, the Milky Way. I'm sure you all being space enthusiasts, I hope you have all seen it. If you haven't, please go somewhere really, really dark and look up at the night sky, and it will be beautiful. This is an image of the Milky Way right next to the ALMA telescope. The ALMA telescope is one of the really modern facilities. It does amazing science, and also the night sky there is very good. But the Milky Way is not the only galaxy, although it is the galaxy we live in. We can see more of them with our naked eye. So if you go out somewhere really dark, again, here is the Milky Way that you should all see. You can see Andromeda if you're in the northern hemisphere, or the Magellanic Clouds if you're in the southern hemisphere. And these are other galaxies. They're the brightest 3 galaxies on the night sky. You can see them with the naked eye. If you have a really good phone and the sky is really dark, you can take pictures of them, or if you have a telescope, you can take pictures of them, and it's a great experience. If you're an astronomer, though, you have access to space telescopes, and you can take pictures such as these. Andromeda is our sort of biggest close neighbor. It's about the same size as the Milky Way, and it's actually very, very similar to the Milky Way. So although we can't like look at the Milky Way from outside in and see exactly its structure, we can look at Andromeda, and this gives us an idea of what kind of galaxy we also live in. Andromeda is a spiral galaxy, a spiral disk galaxy, in fact. So it's flat in 3 dimensions, kind of like a plate. It has beautiful spiral arms and dust lanes and lots of stars, and it's forming lots of stars. It's actually a fairly typical galaxy for the universe. Lots of galaxies look like Andromeda. However, it's not all. There are many, many, many more galaxies apart from the Milky Way and Andromeda, and these galaxies is what I study. So I promised I'll go back to this picture. This is the Hubble Extreme Deep Field, and I think it's an amazing feat of human achievement. If you don't know the story of this image, basically what we did is we shot a tin can in space, called it Hubble Space Telescope, and asked it to point at a very small, very dark part of the night sky. There was nothing there in the night sky. I think I read, at least the way I heard the story, they didn't even know they'll find anything. Someone just proposed to look at the very dark part of the night sky for many hours, and they got this image. Every point here, almost every point here, is another galaxy. They're not stars. These are hundreds of different galaxies that are very far away from our own. And you can see in this image that there is a huge variety of them. You know, they have different shapes, different colors, different properties. They all live very different lives, not just like the Milky Way and Andromeda. However, if you stare at it for way too long, and you also have a keen eye on trying to classify things and finding similarities between different things, you'll start noticing that, in fact, they're not so different from each other after all. And if we look at images like these, we can split galaxies roughly into 2 main types. One is galaxies like Andromeda. These are spiral galaxies. They have disk structure. They all have these dust lanes. They all look very similar. They're just sort of rotated a different way on the sky and have slightly different colors. But they basically all have the same structure. And the second type, very different from those, are galaxies such as these. They're all round, kind of boring looking, but I'm not going to say anything bad about galaxies. They're all great. They're much redder in color and sort of featureless, red, round, centrally concentrated galaxies. So this is not a secret. We knew about this since 1926. Edwin Hubble first looked at a bunch of galaxies on photographic plates and said, hey, look, there's sort of a sequence between galaxies that are red and round and galaxies that are blue and spiral. This probably means something. And he called this the Hubble's Galaxy Classification Scheme, or the two-union fork, where you go from left, these round galaxies, to the right, where we have spiral galaxies that are either completely circular on the top or have sort of a straight bar going through the middle of the galaxy on the bottom. And at the time, we didn't know what this means. But because we're scientists, we're looking at it and we thought to ourselves, well, there must be a way to explain it, right? And one explanation is evolution. Maybe one type of galaxy becomes another type of galaxy. So, Christian, can you pull up the first poll question, please? I want you all to put your astronomer hats on and try to figure out which way do you think this evolution will go, or is there any evolution at all? Any answer is fine. I just want to see what are people thinking. And I'll give you sort of, I don't know, a few seconds to think about it. Meanwhile, I'll just admire these galaxy pictures.
Okay, we'll wait a few more seconds and then let's see what we get. Okay, so I'll share the results. What do you think, Lisa?
Wow, there's actually an even split. I really appreciate people who said there is no evolution. That is actually a good science hat thinking. If you don't know the answer, if you've not been studying this for 10 years, why should you believe me that one thing evolves into the other? And actually, that is the way they thought in 1926. So when Hubble first did this tuning fork, he called galaxies on the left early type and galaxies on the right late type, which to the rest of us implies that the early type ones evolve into the late type ones. When he came up with those names, that was not the intention. That was sort of random. He didn't imply there's any evolution at all. And as it turns out, he was wrong. The galaxies on the right, we think, evolve into galaxies on the left. So choice 2, which is also the most popular choice, is correct. Congratulations, you guys, for knowing everything about galaxy evolution. So the way we now know that the galaxies on the right evolve into galaxies on the left is by looking at their properties. The galaxies on the right, as I said, are spiral galaxies. They're disks, they have spiral arms, they have blue colors, and the last point is important. Their blue colors mean that they are actively forming new stars. For example, Milky Way forms about one new star each year. Other galaxies can form stars slightly less frequently or much more frequently. Some stars can form thousands of stars in a year, but they're all forming new stars right now. The galaxies on the left are instead what we call red and dead. They have their red colors because they're not forming any new stars anymore, and that means in sort of galaxy evolution speak that they have died. So when I say a galaxy is dying, it means the galaxy is stopping forming its stars. And sort of by just drawing a line from one to another, we know that, well, a galaxy formed stars before, it has all of these stars we can see, and then it's not forming stars anymore. So these star-forming galaxies on the right must evolve into quiescent or red and dead galaxies on the left. And the main question of my research and research of all my colleagues and lots of other people is, how does this happen? How do these galaxies form and evolve and become what we see today? And I'm really, really sorry for the next reference. I was going to take it out, but to understand how galaxies form, we need to know that they'll start with a Big Bang. Yep, I'm sorry. So when the universe formed, there was a Big Bang, and everything was uniform. Everything was the same color, the same temperature. There was the same amount of mass and everything everywhere, basically. And what you're looking here is if we took a very, very boring picture of the cosmic microwave background, which is the last snapshot we have of that really early universe. If you have been to an astronomy talk before, you'll know that that's not what the cosmic microwave background looks like. Instead, you see pictures like this. But this picture really exaggerates really, really small differences between different parts of the sky. So the cosmic microwave background has one temperature of 2.7 or something Kelvin. These variations you see on the image are in millikelvins. They're very, very small. But these small fluctuations in sort of how the universe started up gave rise to the galaxies and the matter and planets we see today and us. So I'm going to try playing this video and hope it works on double speed. This is a simulation of sort of galaxy formation run by a supercomputer by some scientists. Oh, there's sound. I didn't expect that. I'm going to stop the sound. So as I said, everything started with these very, very small fluctuations, small sort of overdensities and knots in the very early universe. And where there is slightly more stuff in one place, all the stuff then comes together and sort of attracts each other, and you end up building up more and more matter in one part of the universe. And this matter eventually builds up into a halo, which builds up into a galaxy. And because this particular part of the universe is overdense, there is more other clumps flowing into it, there's more gas flowing into it. And as the gas flows in and then eventually cools down and flattens out, you form a galaxy. So all of the galaxies started with gas and dark matter flowing into these small halos in the very early universe. And the reason I showed you this is to explain this explains the structure of the galaxies we see today. So galaxies are places in the universe where all this matter fell in together in one sort of big well that then became a disk. And they consist of 4 primary parts. The first one is gas and dust. It's much harder for us to see gas, but we can see dust very easily, like the dust in the Milky Way when we go out in the night sky. And this dust sort of correlates with where the gas is. As the gas cools, it ignites and forms new stars. So the second important component of a galaxy is its stars. Last, but well, not last, third, but also very important, is the supermassive black hole. In the center of every galaxy, there is a black hole that has a mass of millions of suns. And this black hole interacts with the rest of the galaxy. It can regulate how the galaxy lives its life. And last, but not least, is dark matter, which I've mentioned in passing, and I will not mention it again. It's very interesting part of galaxies, but we can't see it. We don't know what it is. And it makes trying to understand how galaxies evolve very interesting because we don't even know what they're made of. So this sort of picture is very schematic. You know, I've explained to you how a galaxy can form from a small overdensity in the early universe into something like this over 14 billion years. Of course, it's not as simple. Every galaxies look different, so it means that slightly different things happen as galaxies evolve. And sort of this picture helps us to understand how can galaxies live their lives, but we need to dig deeper into exactly what's going on in these galaxies. And sort of this is what my research focuses on, trying to figure out the transition from a star-forming spiral disk galaxy into this red and dead one. This happens over 13 billion years or so. So unfortunately, I don't have time to sit and watch that happen, although I would like to. So instead, I focus on galaxies that are dying right now. I'm focusing on transitioning galaxies. In ways in which I'm not going to talk about in this talk, we know that these galaxies are either just about to form stopping stars or are currently stopping forming stars. And I like to describe my work as sort of solving, like putting my detective hat on and solving this mystery of what's killing these galaxies using space telescopes. I can't watch this unfold because even the process of dying can happen over millions of years to billions of years. But what I can do is look at the galaxy in a telescope and pinpoint, find like hints of what could be going on based on my science knowledge and what I see in the image. In each of these galaxies, I try to unravel what's going on in its life. So the main question I ask myself is, how do these galaxies die, or what's killing them? So before we talk about how galaxies die, another sort of step away, when I say galaxies die when they stop forming stars, what does it mean to form stars? How can a galaxy form stars? If we understand how stars form, then we can start answering the question of why don't stars form. So this is another simulation. Astronomy simulations are great, which is why I like showing them to people. This is sort of a schematic of how a star could form. So what you're looking at here is a cloud of cold gas, and eventually this gas collapses onto itself and cools down and becomes denser and denser and denser until it ignites and a new star is born. So this tells us that Trying to skip to the next slide. So this happens in places such as this. I hope lots of you have seen this image. This is Pillars of Creation taken by James Webb Space Telescope. It's spectacular, and it's a site of where stars are forming right now. So these are these clouds of cold gas, and as they collapse onto each other, new stars will form and blow away some of this gas. So for example, I imagine this star here in the middle of the image is a star that's just blown away a hole in the gas because it ignited. So if this is how stars form, what's important to remember is that for a star to form, we need gas that will cool down and then collapse to form a new star. And these are three necessary things for a galaxy to stay alive, that these three things can happen. So when we talk about ways to kill a galaxy, we can try to affect each of these ways. First one is gas. If there's no gas, you can't form any stars. The simplest quenching mechanisms just remove, the simplest, I didn't say what that is yet. The simplest ways to kill a galaxy is to just remove the gas from the galaxy. You can achieve that by driving winds. Galaxies have winds just like our planet, and these winds can blow away the gas from the disk so that it can't form any more stars. You also can prevent the gas from cooling by heating it up. For example, if a star explodes in a big cloud of gas, this explosion will add a lot of energy to the rest of the gas, and it won't be able to cool down as quickly. So heating up the gas is another way to stop a galaxy from forming stars. And finally, okay, we have gas, it's cooling down, it's trying to collapse, it's making this sort of already a protostar. If you just stir it up and stop it from collapsing, you can also stop the star from forming. So the last sort of way to stop star formation is to stir the gas up through, for example, turbulence, different motions that stir a galaxy can stop it from forming new stars. So all of these different ways that affect gas in slightly different ways we call quenching mechanisms. Quenching mechanisms are basically, it's a physical process that can stop the gas in some way from forming new stars in a galaxy. So when we look back at this sort of diagram of what I study in my research, we want to understand which quenching mechanism leads from one to another. And the great debate between all of astronomers in astronomy, like in many other sciences, for example, sociology, is the debate of nature versus nurture. We can step back from galaxies and, go back to to people, where we try to understand why people grew up the way they grew up, and it's exactly the same question. So here's a family of UK's favorite gingers. Who your parents are, the way you were born, your genetic makeup will determine how you're going to grow up. If your parents aren't ginger, you're much less likely to grow up to be a ginger yourself. This is the same for galaxies. If the galaxy started up in a certain way, its life will be determined in that way. If it started in a region of the universe with lots of gas in this overdensity, it might have more access to gas as it grows up than a galaxy that started somewhere else. So as for humans, it really matters for a galaxy what are its properties, its initial conditions. But as for humans, if you take two identical twins and put one of them to grow up in Japan and the other one in America, they'll grow up very different people. They'll speak different languages, they'll have different jobs, they might look alike, they might have some similarities, but they'll end up different. And same for galaxies. Galaxies that grow up in two different parts of the universe will have different lives. So the question of nature versus nurture is very important and something I debate with my colleagues all the time. So we split these quenching mechanisms into the sort of nature versus nurture classification scheme. The nature ones we call secular. Doesn't matter why, you don't need to remember this word, but these are mechanisms that depend only on the galaxy itself. What is its mass? What is its shape? How quickly is it forming stars? How much gas does it have? If it has more or less gas, it might, if it has more gas, it'll form stars for longer. What is its supermassive black hole doing? These are mechanisms that if you just took the galaxy and put it in the middle of nowhere and forgot the rest of the universe exists, these mechanisms would still cause it to quench. So a simplest example of one such mechanism is just using up all the gas. So if you imagine a galaxy exists on its own, it's just hanging there, it had some gas from the start, it's forming stars from this gas. So you take a cloud, form a star from it, you've used up that gas. If you go on doing this for billions and billions of years, eventually you might think you'll convert all of the gas you had from the start into stars. So this is one way in which a galaxy can die without any external influence. I like this sort of mechanism because it's very easy to explain. It makes sense. If you run out of something, you can't make any more stars. If you do the maths, it's not actually what happens, because for this to happen, it will take much longer than the age of the universe for a galaxy to die. Galaxies have too much gas to just run out of gas on their own. But it's a good jumping off point. This is sort of the simplistic idea that we can start developing other more realistic ideas from. So another way to kill a galaxy is through a bar that I've mentioned before. A bar is sort of a disturbance in the galaxy's shape that stops it from just rotating like a circle like galaxies like to, and instead stirs up the gas in the galaxy. And I already told you that stirring up the gas can be bad. It can stop gas from forming stars. It will also heat the gas and stop it from cooling down. You can also have quenching from the supermassive black hole in the center. If the supermassive black hole decides to be active in a galaxy, it can output incredible amounts of energy, blowing out the gas from the galactic disk. So what you see here is an example where the black hole is driving these powerful bubbles that heat up and expel the gas from the galaxy, quenching it. There are many more. I can go on for hours and hours about different ways in which galaxies can die. But these are sort of three examples of what people talk about and what I find useful in my research. So these are secular quenching mechanisms. I was a bit sneaky because I took this picture and then I blocked out the rest of the galaxies on this picture. That's not really realistic because galaxies don't live on their own, like we as humans don't live on our own. We're surrounded by other things and other people. This galaxy is a part of Stephan's quintet, another brilliant picture by James Webb Space Telescope of 5 different galaxies that are all colliding with each other at the same time. So it's a bit meaningless to say what could happen to this galaxy if it was on its own when the main event in its life is occurring right now. It's colliding with another galaxy. So these we call environmental quenching mechanisms. The effects of your neighbors, or if you are in a dense part of the universe, you could even be embedded in groups of tens or hundreds or clusters of thousands of galaxies. And being in these environments can really affect how your life as a galaxy proceeds. So one thing I want to talk about more is this act of galaxy mergers or collisions between galaxies, because it's very, very important. It's an important event in the life of a galaxy, and lots of galaxies experience it at least once. So here is yet another simulation of 2 galaxies merging. And this one I think is interesting because it's a simulation of a Milky Way merging with Andromeda, which will actually happen. Milky Way and Andromeda are approaching each other and will merge in sort of 5 billion years. So this is a scientist's interpretation of how this might happen. We have Milky Way and Andromeda sort of right now flying towards each other, and nothing really happens to the galaxies as they approach. But wait and see, a merger can be a very dramatic effect in a galaxy's life. So as they first pass by each other, they already disturb the gas from the two galaxies. You see these beautiful tails of gas streaming away from the two galaxies, and then they part, and then they approach again, and eventually they coalesce. But the winds caused in the merger blow away a lot of the gas, and the merger itself heats up the gas, which will cause the final remnant to be this red and dead or elliptical galaxy. A merger of two galaxies that are so similar in size, like Milky Way and Andromeda, is very effective at quenching star formation because it completely alters the structure of both galaxies and really disturbs the gas in a galaxy. So going back to this sort of question again, I like to go back to the slide because this is what I do. This is my research. We want to figure out if the quenching mechanism that transforms galaxy from one type to another is through nature or nurture or both. And as I said, I look at transitioning galaxies. But what's exciting about being an astronomer in this day and age is that I don't just do it with my own eyes or just optical telescopes. We can look at galaxies in all sorts of different types of light. And this can really, really help. If all we had available to us is optical imaging, it would be much more difficult to understand how do galaxies evolve. We have access to telescopes that can look at galaxies from the longest wavelengths in the radio to the shortest wavelengths in the X-ray. And this is really vital because these wavelengths show us different parts of the galaxy. So here's an image of the Milky Way. This is how you would see a Milky Way with your eyes, if your eyes were really, really good in the optical light. What we see are stars, this sort of yellow envelope of stars, and dust clouds blocking off the starlight of the Milky Way going towards us. But if you had a telescope that can see in the infrared instead of the optical light or some other lights, you would see very, very different structures. Although the structure of the Milky Way in starlight is familiar to us, we might not know that it looks so different in all of the other different wavelength bands. So an interesting one, as I said, is infrared. Infrared light is what is emitted by dust. So here, instead of looking at the stars of our galaxy, you're looking at the dust of our galaxy. And as I said, dust traces gas. So that can help us understand the difference between what the stars are doing and what the dust is doing. If you look in the radio wavelengths, you can actually see the cold gas. So on this image on the top, these are sites of where the stars are forming. This is when the gas is so cold, it can collapse to form new stars. And if you look in the X-ray, you'll see very, very energetic emission from shocks from the youngest stars or from winds. So in my research, what I do is look at all of these different wavelengths and try to figure out what kind of process could lead to, for example, cold gas being slightly different or in a slightly different place from dust and stars, and try to figure out what this means for the life history of the galaxy. So going back again to this image, I think both in terms of quenching mechanisms that I've talked to you about, is a galaxy merging? Is there a wind? Is there a bar? And also different galaxy components. For example, a wind would only affect the gas, but not the stars. So you'd expect a galaxy with an ongoing wind to have sort of normal optical appearance, but a weird infrared one. And astronomers focus on these observations in many, many different wavelengths to try to really piece together the puzzle pieces and figure out the evolutionary history of a galaxy. So I wanted to give you guys a chance to try to put on your detective hats and tell me what do you think is happening with these galaxies. I have two case studies for you. The first one I think is a lot easier than the second, but let's try the first one. And I'll give you a minute to think. I'm guessing you can see how many people voted Christian.
Yeah, it's exciting. Okay, I'll share the results.
Great. Yeah, good. Most of you have been listening.
Yes.
This is good. So yes, this is a very recent galaxy merger. I mean, it's still going on. It's remarkably similar to the simulation I showed you guys. So one of the ways in which you can see from this image that these galaxies will likely quench is you can see the bridge between one galaxy and another, sort of in the blue light. It means that the galaxy on the right is stealing the gas from the galaxy on the left. So eventually the galaxy on the left will lose all of its gas and not be able to form any more stars. So I think the galaxy on the right will quench after the galaxy on the left. That's my prediction, because you can see the direction of the gas being lost, I think. Anyway, I mean, I'm not a prophet, so it might not be what happens, but these are sort of little clues we as astronomers can look at to figure out what's going on. And let's move on to the second case study, which I think is more challenging. So let's see how you guys do. Why do you think this galaxy is dying? I'll make galaxy evolution experts out of all of our viewers yet.
Okay, that's the result. It's more difficult. You could see.
Yeah, it's a difficult question.
Yeah.
I like that you all said that it is not a recent collision. This is actually a tricky one. So all of my research focuses on trying to figure out if a galaxy recently had a merger, even though it doesn't have any obvious merger signatures. So it might have had a recent collision, but yes, you're right. You can't see it. Yeah, I like all of these answers. I've made it tricky because as I said, I'll come back to this. I have made a point that it's useful to not just look at the galaxy in the optical light. So what I've showed you is an image that's actually really hard to find of this galaxy. This is M82. What some of you may have seen is this image. This is the same galaxy not seen in the optical light. So in the green is still the optical image from before. But in other colors, I'm showing you X-ray energetic emission from the Chandra telescope and the dust emission from Spitzer. And although these galaxies' stars look normal, it's blowing up huge amounts of gas as we're watching it. This is a galaxy that we call a starburst. So it recently had a massive burst of new star formation, lots of stars formed in the center. And as these stars sort of form and explode and form and explode, they start driving huge winds that blow up the rest of the galaxy, the rest of the gas from the galaxy. And it's really cool that if you sort of look at this image, you can't see it. Maybe the really careful of you could see that there's like tendrils of dust that we call dust cones coming out. But the moment you look in a different light at the galaxy, you can see that it's going through a very, very dramatic event. So this is why sort of looking at different wavelengths is really useful. And it's still a question of why this galaxy has a starburst. So I mentioned that there's no evidence that it recently had the merger, but one of the reasons a galaxy could start forming so many stars so quickly is if it had a merger. So that we don't know. But currently it's dying because it has these massive winds blowing out the gas. So I'm nearing the end of my talk. I've talked a lot about the evolution of galaxies, and I've sort of sold it as a talk about how galaxies form and evolve, and I've not really talked about how galaxies form, other than a very small interlude into Big Bang Theory. And this is unfortunately because galaxies formed very long time ago, and we can't see that. We can simulate how galaxies form, but we can't really watch them form from using observations. But this is changing, and the future is exciting. This is a good time to be an astronomer. What you're looking at here is a picture from James Webb. Again, there's lots of pictures from James Webb because I'm currently very excited about this telescope. This is a very deep field showing galaxies not only nearby, but some of the earliest galaxies formed in the universe. And the new instruments like James Webb and others are really pushing our understanding of galaxy evolution to new frontiers. The next decade will be amazing for astronomy. Not only we have James Webb, but we have lots of other instruments like LUVOIR that will come out in 2030, I think, or Vera Rubin's ground-based survey that will cover huge areas of the sky to an incredible depth, and other telescopes that are continually coming out and giving us more and more data and showing us galaxies and objects in the universe we've never seen before. And I think in this decade, we might be able to actually start answering the question of how galaxies form, not just how are they evolving right now. And to wrap up this talk, I just want to very briefly give a shout out to two of my favorite discoveries of the past year, past several years. On the left, I'm sure most of you have seen the image of an accretion disk of a black hole taken by the Event Horizon Telescope collaboration. The fact that we could do that is mind-blowing to me. This image is a bit newer, and it's actually showing the magnetic field lines in the accretion disk of this black hole, and we can see that. That is incredible that we as humans could come together as one planet and build a giant planet-based radio telescope and do that. The one on the right is a more recent discovery. It's a galaxy that is the furthest away discovered galaxy so far by the James Webb Space Telescope. So last vote of the night is how early in the universe do you think this galaxy is? I'm sure a lot of you know that as we look at very distant objects, we look at the earlier parts of the universe. So a galaxy sort of that is 4 billion light years away from us, the universe is 8 billion years old at that time, that sort of thing. So how old was the universe when this galaxy was observed?
So careful, we're looking back in time now, right? So so be careful that you don't, it's not a question how old is the universe. So just watch out when you answer the question.
Yeah, I'm not asking the look back time. I'm not asking how many light years, but how old the universe is.
Yes.
At this time.
That's it. Yes. Yeah. That's very nice. You, whilst the poll goes on, that you included the recent Pillars of Creation. I think it's 2 or 3 days oh, that image, right, from James Webb University. Really incredibly beautiful images.
Yeah, what they're doing is incredible.
Okay, I will end the poll and just share it. I think there were some misinterpretations there, but
Yeah,
that was spherical.
fair enough. It's an even split, and I'm sorry I've made the question sort of more challenging. The way people would usually say is this galaxy was imaged, like sort of the distance is 13.5 billion years to this galaxy. I decided to flip it because I think it's, I mean, mind-blowing that the universe at this time is 230 million years old. This is less time than from us to like the dinosaurs.
Yes, yes, absolutely. So that's the correct answer. Yes, there you go. So
yeah, these are the very first sort of steps of the universe, the very first galaxy formed in that young universe, and it's amazing that we can see it. So on my last slide, I'm going to end on this image, which I thought was too bad this talk isn't on the 24th of October, because that would be a really cool coincidence, but close enough. This is the first ever image taken from space by a rocket of our planet. And I just want to end on a note saying that from the time that the humans first sort of became part of space and took this image, instead of just looking up from the planet up to the sky and thinking, what are these stars? Are we a part of that or not? We've gone so far. We've learned so much about the universe, and we're still learning, and it's an exciting time. Thank you all for listening.